All right, let's talk about how computers make sense of the world. Today, we're diving into two really fundamental ways they organize information. We're going to meet two different personalities, if you will. One that builds a grand, detailed structure, and another that just sorts things out as fast as it possibly can. You've seen this, right? It almost feels like magic. Behind your search results, those eerily accurate product recommendations, that playlist that just gets you, there's a really powerful process working behind the scenes, finding all the hidden patterns in a total chaos of data.
And that process, it's called clustering. Honestly, you can think of it as teaching a computer to be a super organizer. It just looks at a massive digital pile of, well, stuff, and automatically creates these neat, sensible groups, all without a person telling it what to do.
Specifically, we're zeroing in on document clustering. The goal here is pretty simple, right? Put similar documents together in one pile and make sure each pile is obviously different from the others. It's how we turn a complete digital mess into a library you can actually navigate. Okay, first up, let's meet our architect. This approach is, super methodical. It's patient. It's all about building a complete, really detailed picture of how every single piece of data is related to every other piece.
So, the architect's official name is single-link clustering. We call it hierarchical because it literally builds a structure, level by level, from the ground up. And agglomerative? That just means it starts with every data point as its own tiny little cluster and then starts merging them. The one golden rule it follows is simple. Always merge the two clusters that have the single closest points between them. That's it.
So here's how the architect's blueprint works. First, imagine every single data point is its own little island. The architect then looks at the whole map to find the two islands that are closest and builds a bridge. After that bridge is built, it remeasures everything and does it all over again, meticulously joining the next closest pair and the next until every island is connected into one single landmass.
Let's actually see this thing in action. We kick things off with the distance matrix. It's just a chart showing how far apart our points A, B, C, and D are from each other. The algorithm scans this whole grid and immediately finds the smallest number. It's a 2, the distance between A and B. So its very first move is to merge them.
So now A and B are one thing, cluster AB. The algorithm recalculates all the distances from this new cluster to everything else and then searches again. What's next? The next smallest distance it finds is a 4 between points C and D. Boom. It merges them into cluster CD. You can see the structure growing, one logical connection at a time.
And there you have it. Once our two big clusters, AB and CD, are finally merged, we're left with this awesome tree-like structure. It's called a dendrogram. This right here is the architect's masterpiece. It's a complete map showing the whole family tree of connections, from the tightest little pairs all the way up to the final grand structure.
Okay, let's totally switch gears now and meet our sorter. If the architect was a patient builder, the sorter is more like a high-speed librarian. It just grabs each item, finds the very first shelf where it looks like it fits, and moves on without a second thought. It's all about speed.
So, the sorter's method is called single-pass clustering, and the differences here are huge. First, it's non-hierarchical, so you're not getting that complex family tree. And it's sequential, meaning it processes items one by one and makes a snap decision for each, all based on a really simple rule called the similarity threshold.
And the method is just incredibly fast. You start with absolutely nothing. The first item comes in, it creates cluster 1. The next item arrives, check it against cluster 1. Is it close enough? Great, it's in. Not close enough? It instantly starts cluster 2. It is a one-and-done decision for every single item that comes down the line.
Now, everything in the sorter's world boils down to this one number, the similarity threshold. This is the only rule that matters. So for our example, we're going to set that threshold at a distance of 3. What that means is if a new item is closer than 3 units to an existing cluster, it can join the party. But if it's 3 or more units away, sorry, it's rejected and has to start its own group. This one number dictates the entire outcome.
So let's watch the sorter go. Our first data point, D1, shows up. Well, since there are no clusters yet, it has no choice but to start its own. And just like that, cluster 1 is born. Easy enough?
Next up, D2 arrives. The algorithm calculates its distance to the center of cluster 1. The distance is 1.41. So is that less than our threshold of 3? Yep, for sure. So D2 is immediately sorted into cluster 1. Done. No need to check any other options. It's already found a home.
Now here comes D3. Again, we check its distance to cluster 1. But this time, the distance is 9.19. That is way bigger than our threshold of 3. So, it doesn't fit.
What happens? The sorter just creates a new destination for it. Cluster 2. Simple as that.
So there you have it, our two contenders, the meticulous, careful architect and the blazing fast sorter. Now let's really put them head-to-head to see how they stack up.
This table really lays out the core differences perfectly. The architect's whole deal is that it has to find the absolute closest pair at every single step. The sorter, it just needs the first good enough fit. And that one difference has massive consequences. The architect is powerful, yeah, but it's slow and it eats up a ton of memory, while the sorter is just lean, mean, and incredibly fast. So the trade-offs are crystal clear. With the architect, you get that beautiful, detailed family tree, and the results are always the same no matter what order you feed it the data. But that precision comes at a pretty high computational cost. The sorter, on the other hand, is built for speed, pure and simple. It's fantastic for huge streaming data sets because it barely uses any memory. But its major weakness? The final clusters you get can change, sometimes dramatically, just depending on the order the data happens to arrive in.
So, what's the big question? Which one is better? Well, the answer, as it so often is in this field, is it completely depends on what you're actually trying to do.
Look, here's why this really matters. If you're a biologist trying to map the complex evolutionary tree of different species, you need the architect's meticulous detail. The extra processing time is totally worth it for that kind of deep analysis. But if you're running a news website and you're trying to categorize thousands of articles as they stream in every minute, you absolutely need the sorter's raw speed. It's all about choosing the right tool for the job.
So the next time your music app builds a playlist that just feels perfect, or your email client magically sorts junk mail from your inbox, you'll know what's happening under the hood. It's an algorithm, whether it's a careful architect or a speedy sorter that's busy finding the patterns. This stuff isn't just theory, it's the invisible logic that organizes our digital lives. So now that you can see it, where else are you going to find it at work?